Okay, so today we start the second module of the course. The second module is very different from the first module. So people who were great with the first module might be very bad with the second module and vice versa. So it's a fresh start. So if any of you had troubles with, for instance, web-based challenges, now we move a little bit into theory. And in particular, we start discussing about verification. So what do we mean by verification? We mean proving that a system is secure. In general, verification is harder than attacking, right? Because if you want to attack a system, you essentially have to find a single flaw in the system. Once you find the flaw, the system is attackable, and so you can try to take advantage of the attack against the system. In the case of the defender, you are in a much harder position, right? Because if you want to defend, you have to ensure that no vulnerability is there, okay? And proving the absence of vulnerability is complicated. And in general, we cannot trust human judgment to ensure that there is no vulnerability, because as a matter of fact, the real-world systems are very complicated. So we want to use some kind of formal automated verification technique, which tells us that within a given model of the system, there is no attack. Of course, security is a complicated story. So in general, you need both hands-on experience, practical security, which is something you got from the web security course. But at the same time, you also need a little bit of expertise on how to model stuff. Because if you can model stuff, you can try to iron out what is the complicated part of the story for security, and you can try to fix problems before someone reports you that a problem is in place, okay? So in general, you need both kind of knowledge. So now we move into the theoretical part of the course. And what I will try to do is to convince you that this is not just a matter of theory, but this has important practical application, okay? And that's why tomorrow we will have a lab class. So we will have a challenge, but this challenge will be on formal methods and will not be a challenge on web security. So I hope you enjoy that. If you have troubles following, because of course the level of the exposition becomes a little bit higher because we discuss theory, please let me know so I can provide some more background for you, okay? So feel free to interrupt me if something is unclear. So just unmute the microphone and speak, okay? So we start today discussing verification in the access control setting, okay? Why do we take the access control setting? We take it for two reasons, okay? We take it for two reasons. First reason is access control is the cornerstone of every secure system. Authorization is a very important aspect. And you know that after authentication, where you prove to the system what is your identity, you also focus on authorization. So after authentication, it comes authorization. So we have to know whether a given access request is granted or denied. And we do this basically on every single system. We discuss this in the context of a web application, but if you think carefully, every single system after authentication has an authorization system, basically. And the second reason why we start thinking about access control verification is that access control systems in general are relatively simple, okay? So analyzing an access control policy is much simpler than analyzing web application code in general. So we start from access control because access control is tiny, and I will manage to tell you a lot about verification of access control just in one lecture. But nevertheless, it is a very important topic. So I want to put your attention on a couple of questions when we focus on access control verification. First question is, what does it mean that an access control policy is secure, right? Because we don't have any, let's say, good notion of security in the first place, right? When we discuss web application security, we said that security means a lot of things. It means that we are protecting against session fixation. It means that we are protecting against session hijacking. It means that we don't suffer from issues related to path traversal and tons of other things. In the case of access control policies, The question is somewhat simpler because the attack surface is much smaller, but nevertheless requires some formal investigation. It's not totally trivial. And then we need techniques to prove or disprove security. So once we have an access control policy and we have formal definition on what it means for an access control policy to be secure, we need a way to either prove security or to find an attack. So to find a way to violate the intended security guarantees. What we will do in this lecture is trying to perform a formal investigation of these two aspects by building on top of a very popular access control model. And the popular access control model we consider in this lecture is role-based access control, ARBAC. So ARBAC is something we already know because a lot of systems we use on a daily basis is based on ARBAC. For instance, if you own a Facebook page, you know that you have editors, you have administrators, you have users. So different people who are sitting on the page have different roles. But now we try to be a little bit more formal and to define ARBAC a little bit more precisely so that we have a common language. So the idea of ARBAC in general is that we have a set of roles. And roles is nothing particularly fancy, it's just a collection of permission. Okay, so you have a way to bind the permission, for instance, to read and write articles, to delete articles, and to access the user list to the editor role. So if you think carefully, a role is just a name which corresponds to a set of permission. And in a role-based access control system, the key idea is that you don't assign individual permissions to user, but you just assign roles to user. So you might have a role which is both a user who is both an editor and an administrator, for instance. In many systems, you can assign just a single role, but in the ARBAC standard setting, we consider a set of roles. So a user might have multiple roles, and in general, these roles might be activated or deactivated at different point in time. For simplicity in this lecture, we assume that every role is always activated. So you don't have any way to attenuate privileges, which of course is not great for real-world security. But for simplicity, we make this assumption. So there is no activation and activation of role, essentially. If you can acquire a role, you can be assigned to that. We will be more clear about this. And after you have this set of role and you possibility to assign role to user, the key point is that the access rights depend only on the assigned roles, not on the user identities. Okay. So if I have Alice and I have Bob and they have the same roles, the capabilities they have are exactly the same. Also, we consider the possibility for roles to be organized in a hierarchy. So if I have that a role R1 is lesser than a role R2, this means that the role R2 is strictly more powerful and it inherits all the permission of R1. ARBAC is a very popular access control model. It is popular, we know, because we find it in many real-world applications. The reason why it is popular is that it greatly simplifies the assignment and the revocation of permission in the case of large organization. Because if you think about a large enterprise, for instance, you might have 10K employees, and assigning individual permission to the 10K employees is a pain, and it's also very error-prone, right? So it's much easier to define just an employee role, assign that role to the single employees, and if you fire someone or if you hire someone, you just assign or revoke the role. And this greatly simplifies and makes stronger the assignment and revocation of permission when you have a large organization. Let's consider a concrete example because we will build on top of this when we discuss the formalism which we use. And we consider the example of university class. So in particular, we can define 3 roles and we can assign permission to these roles. We can have a teacher role who has 2 permissions. So the teacher is able to both create and grade assignments. Then we have a teaching assistant role, which I would like to have populated next year. And the idea of the teaching assistant is that the teaching assistant cannot create assignment because this is a responsibility of the teacher, but the teaching assistant can grade the assignments. For instance, can check your write-ups to see whether the write-ups are good or not. And finally, we have the students. we have a single permission, which is the ability to submit solutions to assignment which were created by the teacher. And so this is the first phase of the ARBAC definition. So we assign permission to role. And then in a second step, we assign user roles. So for instance, in this case of this lecture, we have Stefano, who is a teacher role, while all the other people in the class are just students. Why is it a nice organization? Because next year, we will only need to revise the user to role assignment, but they will never change the permission to role assignment. So I will have new students. Some of you might stay a little bit longer. I hope not. I hope that you all pass the exam. But the key idea is that I don't touch the permission to role assignment. I just touch the user to role assignment. And this is great. But in this discussion, I was assuming something implicitly, which instead is a big problem. And the big problem is who is authorized to change the role assignment? Because in this discussion, I assume implicitly that next year I will be able to revoke the student role from you, and we'll be able to assign the student role to other people. But there is nothing like this in the ARBAC policy itself. So to deal with this problem, there is an extension of the ARBAC model which deals with administration of roles. And this extension is called ARBAC, so administrative ARBAC. So the key idea of ARBAC is that we can use ARBAC itself to handle role assignment and role revocation. So from now on, we uniform the terminology. So I will just say ARBAC because it's easier for me to spell, but there is an extra A in front of that, and you will find this extra A in the slide, okay? So the key idea is that we have a set of roles which is said administrative, and administrative roles have a special power, which is the special power of granting and revoking roles. So by having an administrative role, you can perform changes to the user to role assignment. Okay. So in the previous discussion we had, the teacher role was an administrative role because I was assuming that as a teacher, I'm able to both assign and revoke the student role. And this idea, in the case of ARBAC, is expressed by a set of rules. And we have in particular two sets of rules. One is called the can assign rule, which expresses which role can be assigned by owning some administrative role and under which condition we can assign those roles. And we similarly have the can revoke rules, which express the roles which can be revoked by owning some administrative role R and under which conditions the revocation is enabled. In the version of the model which we consider, which is the standard version of the model, can revoke rules have no conditions. So once you have a role, you have also the ability to revoke other roles with no further checks, okay? So we will see that in the case of the can assign rule, we have some conditions which are required for role assignment. In the case of can revoke rule, we will not have this condition, okay? This is part of the ARBAC standard in its most popular version. Let's try to write down how administrative rules will look like for now using natural language. So we write down these things informally using the English language. So in the case of our classroom, we will define 4 rules. We will have 2 can revoke rule, which are rule 1 and 2. And then we will have 2 can assign rule, which are 3 and 4. So the first can revoke rule says that a teacher can revoke the role student, and the second rule says that a teacher can revoke the role teaching assistant. So that's what I meant when I say that revocation is unconditional. So it means that I don't need to check anything more. If I am a teacher, I can revoke the role student, and I can revoke the role teaching assistant to any user of the system. Then let's have a look at the rule 3, which is a little bit more interesting. Rule 3 says that a teacher can assign the role teaching assistant to any user who is not a student. Why did we define the policy like this? Essentially because we have a conflict of interest in place. Because if you are a teaching assistant, you are able to grade assignments. But if you are a student, you are able to submit solution to assignment. So if you are both a teacher, if you're both a teaching assistant and a student, you might have a conflict of interest because you can submit your solution and then grade your own solution. So for this reason, we put a precondition on the application of the rule, and I say that I can assign the role teaching assistant only to users who are not also students. In the case of the fourth rule, we say that a teacher can assign the role student to any user who is not also a teacher, because teacher already spent a lot of time studying, so you don't want to assign them to the student role. What we will do along this lecture is try to take this example and express it using a formal language. But before we do that, there is an interesting point. So let's assume I wrote this policy. A good question is whether this policy is secure or not. If you think carefully, this is not an obvious task, right? Because in this policy, I'm combining some security consideration because I have a conflict of interest. But at the same time, I have other rules which are not really dictated by security reasons. For instance, rule 4 is not really dictated by security reason, right? It's just a rule which I put because I want to give a specific semantics to my role. And in general, it is hard to say whether a policy is correct or not. Also because I will say that the policy also depends on the user who are already inside the system. For instance, trivially speaking, if there is no teacher in the system, a policy is secure, right? Because I mean, if there is no teacher sitting in the classroom, nothing can happen in the system. So the policy is trivially secure. So in general, defining whether an administrative policy is secure or not is not an easy task. And we will focus in particular on how we can express what is the intended security policy of an administrative policy, and also how can we verify that the policy is secure or not according to the definition which we put in place. Before digging into the formal details, I want to stress a little bit more of what we want to do now, because what we want to do now in this tiny example is something we will do also in the upcoming lecture when we will consider more complicated example. So first observation is administrative ARBAC is much harder to verify than traditional ARBAC. In the case of traditional ARBAC, you have a set of users, and these users have their roles. So you can just inspect every single user and check whether the user has just the roles which are intended for that user. This can be a massive task because if I have 10K employees, I need to scan through 10K users to verify whether they only have the employee's role. But in the case of administrative ARBAC, the problem is much harder than this, because in the case of the administrative ARBAC, there is a dynamic component which comes from the introduction of administrative rules. So in particular, it means that the assignment of roles to user is not a static snapshot, right? It's not something which is stable, which I can verify, but it's something which changes. Because I might have a system where there is no teaching assistant, but eventually some student becomes a teaching assistant because I have a teacher who is taking administrative actions, and this administrative action changes their user to role assignment. So in general, verifying system with an administrative component is much harder to verify static systems. That's the first important point to discuss. And in particular, we will analyze what is the complexity of proving security for administrative ARBAC. The second point I want to stress is that there is no black or white notion of security for administrative ARBAC. In general, we don't have a way to say whether a policy is secure or not, but we need a way to express what are our security goals. And once we make the effort of clarifying what are the security goals, we can say whether the system is secure or not. Importantly, we need also a way to formalize the security goals, because once we have a clear security goal in mind, we need to express these informal security goals we have in mind within a formal language, because once we have a specification in a formal language, we can also build techniques to automatically prove whether the security goals are met or not. And automated verification is one of the key contribution of formal method for security. Okay. So in general, we want to have a way where you can push the button, let your computer run, and the computer eventually will tell you the policy is secure or the policy is not secure. Let's start now discussing about how we model ARBAC. And to model ARBAC, we will make several simplifications. In particular, the ARBAC standard, you can find that as a NIST standard, has 3 components. The first component is called URA, which is an acronym for User Role Administration. And URA is the part of ARBAC which deals with the common task of assigning and revoking roles to users. The rules which we discussed previously about teacher, teaching assistant, and students was an example of URA, User to Role Administration. But the ARBAC standard is more complicated than this because real-world enterprises have complicated requirements. So in traditional ARBAC standard, you can find also a PRA component, which is so-called permission role administration. And this deals with the task of granting and removing permissions to roles. Intuitively, this is a much less common task than performing URA, because in general, once you define a role, the role is somewhat stable. So it's much easier to change the user to role assignment rather than changing the semantics of the role. So you might occasionally need to change the semantic of the role because, for instance, you extend your system so that you have new components and you want to adapt your roles so that these roles also are able to do something over the new components. But in general, it's a task which is way less common than just adjusting the user to role assignment. And the last component of ARBAC is called RRA, which is role administration. And that specifically deals with the management of the role hierarchy. So the role hierarchy, we said, is a way to structure role in a sort of order such that roles which are higher on the order inherit permission from roles which are lower in the order. You might want to occasionally change the hierarchy, but this task is not very common, so we assume that the hierarchy is fixed. Even better, we will assume, for simplicity, in the following, that there is no hierarchy in place at all. And we do that because every time you have a hierarchy, you can essentially compile it away by picking the permission which are in the lower role and making this permission flow to the higher roles. So the hierarchy is great for real-world administration of users, but in our formal model, we will assume that the hierarchy is not there. So the role hierarchy is flat, and if we have something like, I don't know, the teaching assistant is more powerful than the student, we will explicitly compile this away. So in the following, we focus on a single component of ARBAC, which is the URA component. And this is something we typically do when we do formal methods, because real-world systems are complicated. And since we want to have a rigorous way to reason about security properties and ideally to prove the security properties, we will not discuss a lot about proofs in this course because I don't want the course to be overly complicated to you, right? But occasionally we will also refer to security proof. But the idea is if you want to do proofs, the smaller the model, the easier is the proof. So what we do in general when we do security verification is we try to find out what is the interesting part. For instance, in the case user to role administration. And this is the interesting part because it's the part which we take care of more frequently. And we just abstract away from two other components, which are still useful, but require different technique. Okay, so abstraction is important when we do formal methods. We remove out stuff which we don't want to consider, and we try to draw conclusion about the remaining bit, which is small enough to fit into a simple model. Okay? Questions so far? Okay, so if you don't have a question, now we jump into the math. Okay, in general, the kind of math we use in the course is not a complicated math. So it's a discrete math. In general, I assume that you know a bunch of elementary concepts like sets, functions, these kind of things. but I will try to introduce the ingredients we need every time we go through this. In general, this is not simple, you will see. It's apparently easy, but it's not easy at all. And you will realize it that going through the course, but the kind of math you need is simple. So you don't need calculus, for instance, you just need to have some basic notion of discrete math. So let's start to think which ingredients we need to model an ARBAC system. So we make an assumption. We have a finite set of roles, and we have a finite set of users. This is already a simplification, right? Because in general, the set of users might change in real-world system because you might hire people or people might retire from an enterprise. But for simplicity, let's assume we have a finite, fixed set of users and roles. We represent the user-to-role assignment using a set which is called UR. And what is this set? It's a subset of the Cartesian product between the set of users and the set of roles. So in general, is a many-to-many relation, because I have many users who might have the same role, and the same role might be assigned to multiple users in general, okay? So this is just a subset of this Cartesian product. And we define a notation. So given a user U, we let UR of U represent the set of roles which are assigned to this user. So formally, it's a set of roles such that the pair UR belongs into the user-to-role assignment. And this essentially represents you a snapshot of the system. So UR is a snapshot of a given user-to-role assignment. The snapshot can be changed, and it changes by means of administrative rules, as we mentioned. And in particular, we assume that a policy P is a pair which includes a set of can-assign rule and a set of can-revoke rules. So for now, we don't discuss what is the syntax of these rules, but we just assume that we have a policy, and this policy includes the two ingredients we care about when we reason about the URA component of ARBAC. The key idea is that given an initial user-to-role assignment, call it UR0, a policy P induces a set of possible new user-to-role assignment, let's call it URI, which we can reach from UR0 by applying the administrative rules of the policy. So we start from the static snapshot, and then you can think about the static snapshot as the root of a tree, where we start by generating new possible user-to-role assignment, which can be reached by applying any of the rules of the policy. And then recursively, from this new other snapshot, we can further apply the set of rules to modify, again, the user-to-role assignment, and so on and so forth. And you build a big graph of all the possible user-to-role assignment which are reachable from the initial user-to-role assignment UR0, okay? How can we represent the rules of our policy? We consider can assign and can revoke rule. So let's start from can revoke rules, which are easier to explain. We said that we assume that the can revoke rule has no precondition. So once I have a role, I get the ability to revoke other role. So technically speaking, a can revoke rule is just a pair. It's a pair where the first component is an administrative role, and the second component, which we call the target role, is the role which can be revoked. So for instance, if I have a pair, array RT, sorry, there's a typo here. So I have array RT, which belongs to CR, not just R, because R is a set of role. So if I have a pair like this, the meaning of the rule is that every user who has a role RA can revoke the role RT from any other user of the system. So that's unconditional revocation. If you have RA, you can revoke RT from everyone. The case of the can assign rules is more complicated. So if we check the type of the can assign rule is a little bit more structured, because in particular it involves the Cartesian product. But the intuition of the rule is simple. So the key idea is a can-assign rule is a for tuple. Okay, so it has 4 components. The first component is an administrative role, which is the role who is actually able to assign the role RT, which is the target role. So in this case, we're formalizing that every user with role RA can assign the role RT, and the sets RP and Rn are the precondition of the rule. We said that role assignment is precondition, and in particular, we can require that the target user has some roles. So these are called the positive precondition, RP, and the user does not have some other roles, which are called the negative precondition, which is Rn. This might sound to you a little abstract, probably. So let's have a look at an example. Okay, so let's start from the example, and then we will see the semantics. So in the example we considered back then, we had a teacher, and the teacher was able to revoke the role student. How can we formalize this notion? We use a shortcut. We use T to represent teacher, S to represent student, and TA to represent teaching assistant. Sorry, what happened? Teaching assistant. So if you want to formalize that a teacher can revoke the role student, this is simple. We just put a pair, TS, inside the CR component of the policy. And if you want to formalize that a teacher can revoke the role teaching assistant, we just put the pair TA inside the CR component. And this is simple. Then we wanted to formalize 2 other rules. You can find the specification of these rules in English in this slide. And we said that a teacher can assign the role teaching assistant to any user who is not a student. So in this case, we have a teacher with the administrative role. Teaching assistant is the role which is assigned, so it's the 4th component of the tuple. And then the only requirement we have is that the target user must not be a student. So this means in particular that I have to populate the set of the negative precondition with the student role, which is represented by S. Notice that there is no restriction. So in particular, the role teaching assistant can be assigned to any user, provided that the user does not have the student role. So there is no positive precondition here. And similarly, we had a rule which says that a teacher can assign the role student to any user who is not also a teacher. And we formalize that by having an administrative rule, which is a can assign rule, where a teacher T can assign the role student S to any user who does not have the teacher role. And we formalize this by putting the T inside the set of the negative precondition. We said that we start from a static snapshot, which is a user to role assignment. We have these rules, and these rules induce the set of the possible following user to role assignments. The semantics is given using a state transition system. And the state transition system is simple. We will see more complicated example in the next lecture. This is apparently scary, but we will read through this and we will notice that this is actually very, very simple, okay? So given a policy P, which includes a set of can assign rule and a set of can revoke rule, this policy gives us a set of transition, which starting from a user to role assignment I moves into a new user to role assignment I+1. To define how these transitions are possible, we just use 2 rules. The first rule gives the semantics of the can assign rules of the policy, while the second rule gives the semantics of the can revoke rule of the policy. Let's start from the semantics of the can revoke rule of the policy, and then we will dig into the can assign rule, which are a little bit more complicated. So we said that revocation in ARBAC is unconditional. Okay, so we can revoke a role from every other user of the system, provided that we own some administrative role. So let's have a look at what happens. So the way we express this formalism is by means of inference rules. So I don't know if you're all familiar with inference rules. I think I showed you inference rules in the formal language and computability course for any of you who attended the course during the bachelor. But the key idea of an inference rule is very simple. So you can think of an inference rule like, if all the conditions which are on top of the line are true, then we can draw the conclusion which is on the bottom of the line. So let's have a look how now this rule reads. So let's assume we are in a given snapshot UR, so we are in a given user to role assignment. And what is this premise stating? The premise is stating that there is a user, which is called UA, which does have a given role UR, was a role array in this user to role assignment. Then we check into the can revoke component of the policy, and the can revoke component says that any user who has array can revoke RT. What is the connection between these two premises? The connection is that these two premises are predicating both of the rule RA. So in particular, we know that there is some user, UA, who possesses the role RA, and we know that since we have this rule, this user with role RA, we can revoke role RT. And then we know, that's the third premise, that the role RT is indeed assigned to some user UT. Okay, so we have a user UA with role array. The role array allows the revocation of role RT, and we have a user UT with role RT. If we have these three conditions, the user to role assignment can change, and the way it changes is that in the next user to role assignment, we remove the assignment of role of user UT to role RT. Is this reasonably clear, or should I explain that again?
Yes, can you repeat, please?
Okay, so the way we express the semantics is the following. So we use inference rules. In an inference rule, the reading is the following. If all the premises which I write on top of the line are true, then the conclusion which I write in the bottom of the line is also true. So in this case, I want to model role revocation. So when is it possible to revoke a role? If I have a user who is granted an administrative role, this administrative role allows a role revocation, and I have a user with another role which can be revoked. If these conditions are all true, it is possible to revoke the role. So in this case, the first premise tells, sorry, let's start from the second premise. In the second premise, I'm telling that the role array allows the revocation of role RT. And then the first premise says that there is a user who possesses the role array. In particular, we know that the user UA possesses the role RA. And then we know that another user UT possesses the role RT, which is a target role, is the role which can be removed according to the can revoke rule. Since we have these three premises, it is possible for user UA to revoke role RT from user UT. And so the current snapshot of the system UR can take a step and evolve in a variant of the snapshot where the role RT is revoked from the user UT. Is it clearer now?
Okay, fine, thanks.
An important bit, which I gave somewhat implicit in the discussion, is that if you notice some variable in the premise, the variable is existentially quantified. So for instance, if you look into this premise, we have a user UA, but there is no reference to UA in any part of the conclusion. So what we are saying this is that there exists a UA such that blah, blah. Okay, so everything which is not bound in the conclusion, so everything which does not occur in the conclusion, is implicitly assumed to be existentially quantified. So it suffices to have a single user UA with role RA, and then I can perform this revocation step. Okay, so keep this in mind, because we will use inference rules quite a lot in the rest of the course. Okay. Let's have a look now into the case where instead we assign a role. It's a little bit more complicated, and it is a little bit more complicated exactly because assignment of roles is somewhat preconditioned. So let's have a look at how these rules look like. So we are in a given static snapshot, UR, and we take a single computation step, and UR is extended with a new role assignment. In particular, after this computation step, UR is extended such that the user UT is given the role RT. Okay, so this is role assignment. A new role is introduced to a given user. How is it possible to perform this step? We have to think about the semantic of the canAssign rule. So this assignment is possible for the following reason. We have a rule inside CA which indeed assigns the role RT. Notice that we use RT both here and here, and this is not coincidence, right? This is exactly because RT can only be assigned if we have a canAssign rule which indeed assigns that role. Okay? So what are the conditions for RT to be assigned? We need for sure a user who possesses the administrative role RA. And this requirement is formalized by the first premise. So in the first premise, we say that we have indeed a user UA who possesses the role RA. And another premise we need to assign the role is that the role is not assigned already, because if the role is assigned already, there is no reason to assign the role again. And in particular, the last premise here is telling us that the role RT was not previously granted to the user UT. Okay. So to sum up, for now we said, after a single computation step, the user UT gets a new role RT. Why this is possible? It is possible because RT was not previously granted to the user, which is this premise. It is possible because we have a canAssign rule, which indeed assigns the role RT. For this rule to be activated, we need a user who possesses the administrative role RA, and this is also possible because for the first premise, we know that we have a user UA with the role RA. So then we just need to check two further conditions. And the two further conditions we have to check is that the precondition of the canAssign rules are satisfied. We said in particular that the canAssign rule has a positive set of positive precondition, which is a set of roles which must be assigned for the role to be activated, and a set of negative precondition, which are a set of roles which must not be assigned for the rule to be activated. In this case, we are assigning the role to the user UT, sorry. So UT is the user to check. And to require that the user UT satisfies both the positive and the negative precondition, we have the third and the fourth premise. The third premise says that all the roles in RP are roles which are indeed assigned to the target user UT. And this other premise tells us that also the negative preconditions are satisfied, because if we take the intersection between the negative precondition Rn and the set of roles which are assigned to UT, we get an empty set. So informally, we're saying that the user UT has all the roles in RP and none of the roles in Rn, which were the condition which we informally required for a role assignment to take place. Is it clear, or are you still confused about how we should read these rules? We pick some water, so you can think a couple of more minutes about this slide, and if something is not clear, I will explain again, okay? Okay, so questions? Is everything clear? Okay, so as you see, we are essentially building on top of very simple math because we are using just a little bit of sets, right? And this is discrete math because we are modeling a system where we take a step from a discrete state into another discrete state. So the rules might look scary for you because maybe you don't have familiarity with the inference rules. But what we formalize is a very precise description of the intuitive semantics of ARBAC rule. Notice that the transition which we wrote have this policy component P over the arrow, because depending on the policy, you get a different transition. To avoid overloading the notation too much, we typically omit this subscript P when this is not relevant or it is very clear from the context. So if there is no ambiguity on which policy we are considering, we don't write down the subscript P for simplicity, okay? Okay, so now this was the example we were discussing, okay? So we've seen how we can start from a policy which is expressed in a natural language, English, and we translate it into a formal language of can revoke and can assign rules. And what we said is that given an initial user to role assignment, this set of can assign and can revoke rules induce a set of possible future user to role assignment which correspond to evolution of the system by results of administrative action. Now there is a very interesting question is, okay, let's assume we have this nice model. So in this nice model, we have a static snapshot. We have rules which tell us how the static snapshot can evolve. The question is, can we formalize when the policy is secure? So can we state explicitly what are our security goals? And if we do that, can we reason about them? So do we have an effective technique to reason about them? I show you an example which is given in this specific case. And the specific case is the one we're considering of a classroom. So in the case of a classroom, my security goal is that there is no conflict of interest. No conflict of interest means that I cannot have a student who is able to grade his own assignments. How can this happen? It happens, if you recall about our policy, if I have a user who owns both the student and the teaching assistant role. What I can show is that given this initial configuration, so in this configuration, we have a user Alice, who is a teacher, and a user Bob, who is a student. I can show that given this initial configuration, And given the rules which we gave for the policy, this system is not secure. Because by starting from this configuration, I can reach a configuration where we have a conflict of interest. How can we do that? We can do that by applying the semantics, so by making this user-to-role assignment evolve into future user-to-role assignment. So on the first line, we see an evolution of the system where Alice revoked the role student to Bob. So when we move from here to here, we are removing something from the user-to-role assignment. And the way we can, the reason we can do that is because we said that the teacher role is able to revoke the student role. Then we have another evolution step. And in this second evolution step, what happens is that Alice, who is a teacher, grants the user Bob the role teaching assistant. Why can it do that? Can do that because Bob does not possess the student role. And we said that not possessing the student role is a necessary precondition to acquire the teaching assistant role. So in the first configuration, Alice could not assign the role teaching assistant to Bob. But by making a first step where the role student is revoked from Bob, Alice becomes able to also assign the role teaching assistant. After that, since the role student can be assigned to anyone who is not a teacher, Alice can also assign the role student to Bob. In particular, Bob is a teaching assistant, so Bob is not a teacher. This means that the rule can be applied. So after 3 steps, we are able to notice that our initial user-to-role assignment evolved into a different user-to-role assignment, which is not nice to us, because in this new user-to-role assignment, we have a conflict of interest that we don't want to have. Okay? So essentially, we can formalize security as reachability. So we can formalize security by saying that we must not be able to reach a state where something bad happens. Okay? And this is a very common approach to security. We discussed a simple example. In this simple example, we said, okay, we don't want to have conflict of interest. So we are saying that we don't want the role teaching assistant and the role student to be assigned at the same time. But if you think about different policies, you will realize that many different security requirements might come to your mind. If I move to a different setting, for instance, an hospital, I might have completely different requirements. And if I move into, I don't know, an enterprise, I might have even different requirements again. What is interesting is that once we do formal methods, you typically try to abstract away from as many details as possible. And what you typically try to do is to find a good definition of security. And the good definition of security for the case of ARBAC is called the role reachability problem. The role reachability problem is very easy to formalize. So given an initial user-to-role assignment, call it UR, a policy P, and a goal RG, which is called the goal, the role reachability problems amount to checking whether there exists a new user-to-role assignment, call it UR prime, such that UR can evolve into UR prime after an arbitrary number of steps. That's the meaning of the star here. Like in the case of regular expression, star means iterate 0 or more times. So it is possible to reach this new user-to-role assignment UR prime. And what is interesting in UR prime is that the goal, RG, is assigned to some user of the system. If you think carefully, this does not look like a great property, right? Because I pick a role, and I really want to know whether this role can be assigned to any user of the system. Apparently, this property is very weak. For instance, let's assume there is a dangerous role, like in the case of university, the role rector. In general, it doesn't make any harm if the role rector is reachable in the university, because indeed the university is supposed to have a rector. The problem is whether the role rector is only assigned to the intended rector, in this case, Michele Bugliesi. So just the fact that the role can be assigned to some user seems to give a very weak security property. Instead, we can show that this role reachability problem, which sounds very weak, is a very useful problem, because by solving that, we're able to resolve many other problems which have an important practical impact. I want to show you a few examples of why the role reachability problem is useful, and the key idea for that is a reduction argument. So for any of you who are familiar with my computability course, we discussed a reduction a lot during that course. And the key idea of reduction is that you have a problem and you transform the problem into a different problem, such that by solving the new problem, you're able to solve also the original problem. And now we will see how many useful problems for security can all be reduced into an instance of the role reachability problem. Let's consider an example. And the first example we consider is the example we've already seen somehow. Because when we discussed about conflict of interest, in the case of the university classroom, we said that the role teaching assistant must never be assigned together with the role student. We can show that this kind of mutual exclusion property, which asks whether two roles R1 and R2 can never be assigned together, can be reduced into role reachability. So if we are able to solve role reachability, we are also able to solve the mutual exclusion problem. The encoding of the problem of mutual exclusion inside a role reachability problem is very simple. So the key idea is we introduce a fresh role, RG, which is our goal. So that's the goal that we want to reach, okay? So that's the part of the role reachability problem. We assign this fresh role. This is fresh in the sense that it is not assigned to anyone, and this does not occur in the policy, okay? Let's give it a fancy name, call it goal. Then we create a new role, R hat, which is assigned to some user U. I don't care who is the owner of this role. I just want that a user possesses this role. And then I introduce a new can assign rule, which says that if the rule R1 and R2, which are the roles which are not supposed to go together, are assigned together to some user, then the role RG is also assignable. If we show for this policy that the role RG is assignable, then this certainly means that also R1 and R2 are assigned at the same time. This is because we have a single rule which assigns RG, which is not initially assigned. So if RG is ever assigned to some user, it means that that same user also possesses R1 and R2 at the same time. This role R hat is a technicality which is needed to require that this rule can actually be activated. Because for a rule to be activated, I require a user to be in an administrative role. So by creating this guy here, R hat, I ensure that this rule is actually activatable. So if I can solve the role reachability problem for this encoded policy, I can just return the answer to the role reachability problem to answer the mutual exclusion question. Is it clear to you?
Sorry?
Not clear?
Sorry?
Yeah, speak.
Okay. What's the meaning of ARBAC? I didn't
So
understand.
ARBAC is just a new role which I create. And the only role of ARBAC is to ensure that this can assign rule can actually be triggered. Because for a can assign rule to be triggered, we must ensure essentially a free condition. We must know that there is a user which satisfies all the positive precondition, satisfies all the negative precondition. In this case, we don't have any. But then importantly, we must also require that there is a user who is the administrator who can actually fire the can assign rule. So to ensure that an administrator is always there, so that if R1 and R2 are ever assigned together, the administrator can also assign RG, we create this new administrative role RHAT, and we assign it to some user of the system. I don't care who is the owner of this role. I can even assign this role to every single user of the system. The important bit is that I have at least one user who possesses this role at every single time. Is it clear?
Yes, thanks.
Other questions? So this is a sort of secret sauce when you do formal methods. You typically have many different kind of queries, security questions you have in mind, but you try to reduce this complicated security question to a simple security question which you can formally study. In our case, the sort of holy grail for security and access control is the role reachability problem. Why I say that this is a sort of holy grail? Because I can show you that many other useful problems can be reduced to role reachability. We consider mutual exclusion here, but now we consider a new problem, which is called bounded safety. Bounded safety is a problem which comes to our mind very naturally when we think about role-based access control. And the question for it is whether a given role R can only be assigned to users U1 UK. We already mentioned this point when I said that in the case of the university, we expect the role rector to be reachable. But I want this role rector to be assigned to a single user with Michele Bugliesi. And if role rector is assigned to some other user of the system, I have a security violation. How can I express this in terms of a role reachability problem? We need to be a little bit more careful than the previous example, but encoding is still not very complicated. So again, as a first step, we create a fresh role, RG, which is going to be the goal role of the role reachability problem. Then we assign a new irrevocable role, RHAT, to users U1 UK. Why am I assigning this fresh role to users U1 UK? Because I want to distinguish this user U1 UK from all the other users of the system. This is very intuitive because the bounded safety question eventually predicates about this user from U1 to UK. And when I create a new can assign rule, and let's have a look at how these rules look like. So the rule is activated by RHAT. This is the less interesting part of the story. It's just a way to ensure that the rule is somewhat activatable, because we have U1 UK, which indeed have this role. The interesting part of the story is here. So the role which we assign is RG, which is the goal. So also this is not too surprising. What is surprising and nice is the way we use the positive and the negative precondition of the rule. So in this case, I say that RG can be assigned to which users? I would like some of you to answer to this question.
I think that it can be assigned to users that has a role R and does not have role or hat.
Exactly. And why do we like that? We like that because if I have a user who has role who has role R and does not have role R hat, it means that there is a user with role R which is outside of users U1 UK, because the users U1 UK are the only user who are granted the role R hat. So if I have a user who has the role R, which is the role which we mentioned in the bounded safety problem, but does not have the role R hat, so is a user with the role R, but is also a user who is outside of the intended group of user U1 UK, then we have a problem. And the problem is shown by the fact that we are actually able to reach role RG. So if role RG is reachable, it means that the system is unsafe. So if the role reachability says that the role is reachable, we want to answer unsafe. And if the role reachability says that the role is not reachable, we want to answer safe. So once we solve the role reachability, we just invert the answer to role reachability, and we have a result for the bounded safety problem. Clear? Let's consider yet another example, which is a property which maybe we didn't think about, which is called availability. Availability means that a given role R must always be assigned to the user U. Put it differently, are we ever going to have a rector in the university? So is it true that the role rector is always assigned to user Michele Bugliesi, for example? To answer this question, we can again rely on the role reachability problem. As usual, we create a fresh role, RG. We create a new role, R hat, which we assign to the user U, which is the user we are predicating upon, okay? And we introduce a new can assign rule of a given format. Again, the first component is not interesting. It's just needed to ensure that the rule can indeed be activated, and the rule can be activated because we have a user U with the role R hat, which is always assigned. The role which is assigned is RG. This is not surprising because this is the role we consider in the role reachability problem. What is interesting, again, are the positive and the negative precondition. In particular, notice that this rule is saying that if we have a user who has role R hat, and the only user in particular is user U, so if the user U does not have the role R, which is the role which must be always available, then we can indeed assign RG. So if we're able to reach a configuration where user U does not have the role R, role RG can also be assigned. So the role reachability problem can be solved. So if the role reachability problem can be solved, it means that the system is unsafe. If instead the role reachability problem cannot be solved, it means that the system is safe. So as in the previous slide, after solving role reachability, we can just invert the answer, and then we can conclude security or insecurity. Now the interesting question, what is complexity of role reachability? So we said that role reachability is a fantastic tool because by using role reachability, we can encode as many security queries as they come to our mind. The problem is that role reachability is extremely hard to verify. In particular, if you think carefully, the total number of possible user-to-role assignment is bounded above by 2 elevated to the product between the number of roles and the number of users. Why is that? Because every user of the system can have up to R role, right? So you have a combinatorial explosion here coming from the fact that you have a bunch of users and that each user can have sets of roles. This is the exponential blow up. So in particular, every user has 2 to the r possible set of roles in the worst case, which correspond to the set of roles you can actually build. But since you have u user inside your system, you pick 2 to the r and you elevate it again to u. So it's 2 to the r to u, which is, by simple math, equivalent to 2 elevated to r multiplied by u. This is super big, because if you pick just 3 roles and 30 users, which is nothing, right? Because if you think about real-world organization, they have tens of roles and thousands of users. But if you pick just 3 roles and 30 users, you get 2 to the 60 possibilities. And 2 to the 60 is a really big number, because it's 10 to the 18. Indeed, we are not going to do this proof, but it is possible to prove that the computational complexity of the role disability problem is p-space complete. What is p-space? Is the complexity class which goes beyond NP. So you're familiar with NP complete problem, and you already know that NP complete problems are tough to solve. Role disability problem is even worse than NP complete. It's p-space complete. If you're curious about what p-space means, you can look into Wikipedia, and you have a nice discussion of all the complexity classes. But in general, the answer is we cannot solve the role disability problem in an efficient way. So I spent a lot of time here to tell you, okay, we want to formalize stuff. After we formalize stuff, we can encode the security in a fancy way by having the role disability problem. But in the end of the day, role disability problem cannot be solved. So why are we wasting time? And the question is, we are not wasting time, because we have techniques to deal with the scary algorithmic complexity of role disability. I mentioned 3 examples here in the slide, because this problem has been studied quite a lot in the literature by security researchers. And we have essentially 3 recipes to deal with the complexity. First recipe is, we don't use ARBAC in its full glory, but we use restricted fragments of ARBAC. So we disable some features of ARBAC, which are contributing to this scary computational complexity. So rather than having full-fledged ARBAC, we consider weaker access control model with less expressive power. And by considering this restricting fragment, it's possible that role disability problems gets simpler. So the complexity drops down. We will mention cases in a few moments. And this is an interesting avenue for 2 reasons. First reason is, if you are the designer of an access control system, you might be aware that your access control system is too complicated, and you might deliberately choose to deploy a different system which is easier to verify. More pragmatically, if you are using ARBAC in its full glory, but for some reason your policy is not making use of some features, you might still fall into the restricted fragment. So it might mean that although ARBAC in general is intractable, the policy you wrote is actually simple to verify. So this result is useful both for designer of access control system and for end users or policy writers, okay? This is one avenue. Second avenue is, we don't perform a fully accurate analysis of the ARBAC policy, but we rely on approximating techniques. What does it mean, approximated? It means that admit some false positive. So if the role is not reachable, I give you a security proof that the role is not reachable. But if I tell you that the role is reachable, I might be wrong, okay? Why is this useful? Because eventually we are making wrong results on the safe side, okay? So if I tell you that the role is reachable, that might be a problem to you. And so you might conservatively assume that if my analysis tells me that this is maybe reachable, I will assume that this is reachable and that I have a security flaw. So this is a very common technique in general when you verify security. So either you prove the absence of vulnerability, or you get an error that vulnerabilities might be there, but you might have false positive. Last possibility is We don't drop algorithmic complexity, like in case number 1. We don't approximate the analysis, like in case number 2, sorry, but rather we perform an aggressive pruning of the ARBAC policy. So we find a way to pick a real-world policy and to shrink it a lot, so that despite the computational complexity, which is intractable, we are still able to analyze the system because the system is very, very small. So if I'm able to reduce a policy to a system with, say, 2 roles and 3 users, I'm still p-space complete, but the number of possibilities is so limited anyway that I can then explore all the possibilities. All these research lines were very successful, and we have results on all the 3 research lines. I don't think I will be able to tell you everything I want to tell you in this lecture, but I will continue tomorrow and I will complete the teaching material. So let's go on a little bit more. And we discuss in particular now the restricted fragments of ARBAC model. There is a very interesting paper, which I link you, which made the effort of trying to understand what are the key enablers of the algorithmic complexity of ARBAC verification. In particular, I want to mention a couple of results. The paper presents full details, so we have many more results. And I think these 2 results in particular are very interesting, at least to me. First result is telling you that if the policy does not make use of negative preconditions, so if for all the can-assign rule we have Rn equal to the empty set, then the complexity class of role disability problem is significantly easier. In particular, the problem is P, so can be solved in polynomial time. Why intuitively we have this? Because if there is no negative precondition, intuitively, assigning role is always the good choice. So you can always assign roles up to saturation. So you assign to all users as many roles as possible, and you can eventually check whether a given role is reachable. So since assigning roles is always the good choice, complexity drops down a lot, and you can show that the problem can be solved in polynomial time. Of course, this is not a formal proof, but I wanted to give the intuition on why, by removing negative precondition, you are able to drop complexity that much. Perhaps surprisingly, we can also show that if a policy does not allow role revocation, so if the set of can revoke rule is empty, then the complexity class of role disability becomes easier, so it's not p-space complete anymore, but it is still NP complete, okay? And intuitively, this is the case, because by preventing role revocation, you are reducing the number of states you need to explore to draw conclusion, right? Because once you assign a role, you cannot remove the role. But on the other hand, you are still forced to make choices. So assigning the role can be a good option or not, because you still have the negative preconditions there. So removing the negative precondition simplifies the problem of role disability more than dropping role revocation. I think we are going to discuss this tomorrow, okay? Because I think I told you already a lot of things, because I have less slides than usual, but the slides are very dense. So I think I gave you a lot of material already. So I will still upload the slide, but I will complete the explanation of the slide tomorrow. And tomorrow we'll also assign you a new challenge. And the challenge is a formal method challenge. So it's a challenge on verification of access control. So I hope you have fun with this. So it's a way to make you comfortable with the practical implementation of the notion we discussed here, okay? So before closing the lecture, I would like to ask you a couple of things. First of all, if you have questions, please pick up. Second thing, if you think that the lecture was too hard to follow, please tell me about this. Okay, so if you don't have questions or comment, we can close the lecture. Tomorrow we will complete the missing slides, and then I will give you the assignment.